Hi class, this video is going to help with 9.1, which is our introduction to a limit. And like, what is this idea of a limit? Okay, I'm going to share my screen. All right, so this is section 9.1 in the book we're using right now, or 2.1, depending. Okay, so the notation looks like this. It's going to be LIM, or limit, as x approaches some constant number c, okay, or something. Of the function. This is kind of what we're doing as a limit. Basically, we're saying like what's happening to our graph and to our function as we get to a specific x value number. So if f of x is close to a single real number L, whenever x is close but not always equal to, that is the idea of our limit. So we're going to get close to a value. Maybe it's like those asymptotes, right? You get close and close and close and close to something, but no, don't touch it. That could be a limit. Now it could touch it as well, but the existence of a limit, C, that's our number it's going to, or the value of the x, okay, has nothing to do with the value of the actual function at that spot. So we have an actual value that could be undefined, but we're looking to see what are we doing as we come to that value from one side and from the other, okay? So this says the existence of a limit at C has nothing to do with the value of the function at C. C, I'm like trying to read what I wrote there. Looks like mag, but that's not right. May, that's may. I don't know why the Y has a little thing. Okay, may not be in the domain of F. However, the function must be defined on both sides of C. So if you want to pause and write that down, go ahead. But let's look at a graph here and kind of this idea. I think I can click it. Yeah, there we go. And this idea. So this is the graph of f of x equals x plus 2. So I have values. I put in 0. That's up at 2. I put in 1. That's at 3. I put in 2, and that's up at 4, and so forth. What is the limit as x approaches 2? And this symbol means from the left. So what is the limit as x approaches 2? Here's our 2, and we're coming in from the left. What's happening? What are we going to on this value? I kind of didn't draw it exactly perfect, but we're going up here to 4. That's what the left side's doing. Our graph is going to 4. So this is saying the limit as x approaches 2 from the left. Now this one says from the right. So here's our x is 2 again. What are we doing as we get closer and closer to x? We're also going to 4. Okay, so both sides are going at 4. From the left and from the right. So some of your homework will say like, you know, where is it headed on the left? That might be different from left to right, which I'll show in my next example. So if our left and right are going to the same number, then we can say the limit as x approaches that 2 of our function x plus 2 is equal to 4. Okay? My dog's going to bark a little on my video for us. Now here's an example of one that might be different from left to right here at this 2 spot. Okay, can you see that we're coming into a different number from the left to the right? And that's what I mean by the left and right have to be the same for that limit to exist. Okay, so let's look at this first one. This first one says, what's the limit as x approaches -1? And we're just calling this function drawn here f of x. Okay, if we're approaching -1 from the left side. Okay, so from the left, as we approach this -1, what number are we going to? 1. Okay, as we approach -1 from the other side, whoop, it's still going to 1. So the graph went to the same spot there. So this limit exists, okay, and it is equal to 1. So as you approach -1, it equals 1. So for that same graph, let's see if I think I can see the graph and my notation here. The limit as x approaches 2 from the left. So here's 2. As we approach from the left, where are we going? 1, 2. We're going to 2. Okay, it's open, means we can't be at 2, but we're headed to 2. So from the left, we're headed to 2. We don't care what the value is exactly at 2. We're just saying it's going to 2. Okay, on the right side, so the limit as x approaches 2 from the right. So this is going to 1. So when I say, what is the limit as x approaches 2 without the plus or minus, it would not exist because the left and the right side aren't going to the same number. Okay, what is the actual value at that spot? This is our notation we should be pretty used to. Oops, I did skip that one up here, but that's okay. So f of 2, what is the actual value? It would be that closed in spot at 1. F of -1 is at 1. So the left and right limit were the same and the value. They're all different. So what has to be the same for a limit to exist? Left side, right side have to be going to the same number. Does it matter the value at that spot? No, doesn't have anything to do with the limit. Okay, so just for your notes, you're welcome to pause and write this down, but this is the idea here. The limit as you approach a value from the left and the right have to be equal. That's all this is saying. Okay, so you're welcome to pause it. That's theorem 1, right? So if and only it exists if and only if the left and right go to the same number. Do we care if there's a value, if the value is that same one? No. I swear I had one. So at this -1, if I would have had an open dot and then like a closed dot up here, we would still say the limit's going to 1. Both values are going to 1, even if at the exact one, the value was somewhere else, which you will see in your homework. Okay, so theorem 2. Basically, the next kind of idea is from a function. Okay, theorem 2 and 3, I didn't write them down all the way. Yeah, I said, look at page 100. I'm like, oh, it's hard to tell you to look at a page from the online book. Let me grab my book. And I can't remember if that's from my other one or not. Okay, let me look. I don't think it's from page 100. Boo, boo, boo. So these are our properties of limits. I hit my camera. There we go. And you're definitely welcome to pause it. This is page 465 in the textbook I'm using now. I used to just use the Business Calc textbook, but this one actually works for both Math 1000, not 1000, finite or business applications and Business Calc. So I went to one that works for both. Basically, this is a list of a bunch of different rules we can do with limits. So the first one is like, okay, if it's a constant number, so basically if you're approaching, x is approaching some number and this is a number, it equals that number. That's kind of weird, but that's how it works. If you have just an x, you're actually going to take that value and put it in, and so you get out c. So for example, it might make more sense this way. If I want the limit as you approach x, so the function is y equals x, then whatever value you're going to, the c value is what you're going to go to. So take it for this one. As we start to do more, you'll be like, oh, okay. This one is saying if you have two things being added, this is amazing. This is really helpful. Then you can take the limit of each one separately and add them. Okay, same idea for subtraction. So if they're minus, I can take the limit of this one, the limit of this one, subtract them. Okay, So this will be our function notation. The other one is if you have a constant k, so if I'm timesing something by 3 or 2, basically you can take the limit and times your answer by that number. So being able to pull out a constant like a factor is awesome. Okay, if we're timesing, same idea. We can split them up in times. If we're dividing, we can split them up as well. If we have a function under a square root sign, then we can also still do the limit under the square root sign. That one we don't see quite as often. Okay, so again, I told you the page number. If you want to pause and write those all down, you sure can. Okay, so let's look at some examples. Oh, I showed my work already, but that's okay. So this is a huge idea. So we have 3 main ideas for business calc. Limits is one of them. So what is this saying here? It's saying the limit as x approaches 2 of this function. So what could I do? I could graph it, go over to the number 2 and see where it's headed. Or you could put that number into the function. That is one of our theorems that allows us to do that. So I'm going to go, okay, 2 to the third minus 5 times 2 minus 1, which you can see I wrote out here, equals -3. So this limit is going to -3. Okay, next one. Under a square root, same idea. You just plug in the -1. So -1 squared times 2 plus 3 is going to give me 5. Okay, and this one comes from property 8 that we just saw in theorem. Oh, wait, no, that's theorem 3. This is in theorem. Well, I think that should say theorem 2 because, and this one too. Or does 8 the one that says plug it in? Yep, theorem 3 is the one that says plug them in, that allows us to do this. Okay, so next one. Okay, we have to watch for 0 in the denominator. This is what's going to get you. This is where the tricky part comes. So I have a 4. I put the 4 in. That's going to give me my limit. So I put the 4 in the top. 2 times 4 is 8. On the bottom, 3 times 4 plus 1 is 13. So I have 8/13. If I would have had a 0 in the denominator, then I would have had issues. I can't actually find the limit with this theorem if I have a 0 in the denominator. Another one you might see is one that is a piecewise function. So it's saying, okay, if x is less than 2 or greater than 2, you have these different functions. So if I'm asked, like, what's the function doing at 2 from the left? So which one represents from the left side of 2? Less than, right? Those are numbers on the left side. So we would use this function and plug in our 2 value to get 5. Okay, then the next one is the same kind of idea, but from the positive. So we know that that would put us at this function because those are numbers greater, and that would give us 1. So does the limit exist at 2? No. The left and right side don't equal. So no, the limit does not exist at 2. Does the value exist at 2? Well, we don't have a line under either one. If we did, then we could find the value, but the value doesn't exist. It only gives us the left, the right, and nothing at 2 for us to be able to solve. Okay, so the next kind of idea is, what if I have a 0? Let me see if I can get that to just a little better. This is called indeterminate form, and this is the form of 0 over 0. Okay, if I have something like 2 over 0, it's undefined, like it can't be solved. But in limits, if I have an indeterminate form, it's just what it means, indeterminate. So you can't, whew, I don't know if I'm done sneezing. You can't decide. So I think I want to skip to an actual problem. Phew! Usually I sneeze super loud and would have like blown your eardrums away. I made a video last semester that did that. Whoops. Okay. So, oops, that's still the theorem. I just want to look at the actual examples. I just think it'll make more sense. Okay, maybe. All right, here we are. So if we're looking at this function here, and I put in the number 1, I would have 1 minus 1 or 0 on top. 1 squared plus 1 is 2. So this one is not in indeterminate form. The answer is 0 over 2, which is 0. Okay, what about this one? What if I would have had a minus in that denominator? Well, then I would have put in that 1 value, 1 and 1, and I would have got 0 over 0. So basically, it told us nothing. Okay, this was a theorem that allows us to like find our limit with this shortcut without graphing and trying to see where it's going. And we can't tell. So if we're in indeterminate form, you need to either factor or multiply by a conjugate, which is crazy. Okay, so I'm going to factor this. The top will become x minus 1. The bottom is x minus 1x plus 1. Then you can see that these minuses are the same, the x minus 1, and I have 1 over x plus 1. Now, where is this as you approach 1? You put the 1 value in, the limit as it approaches 1 of the factored and reduced is going to be 1/2. So if it's an indeterminate form, look for factors. Okay, I think you have one that doesn't use factors, that uses another method, but almost all of them are just, you have to factor. Like you can't see it right now. So 0 over 0, not the same as 0 over a number or a number over 0, right? 0 over 0 is different. It's indeterminate. Okay, so here's one where the limit just doesn't exist. So I wanted to show one of those. So you put in the 1 value and I get 2 on top, but I get a 0 on the bottom. Not indeterminate. I don't need to factor and cancel. Well, I can. I can factor and cancel, and I'm still going to have a 0 in the denominator. So this limit just doesn't exist. Okay. Okay. There was one. Oof, this is just it. I know it's labeled like problem 2 or something random, and we were not on problem 2. This was just what I used to do in class. Is I would bring in challenge problems the next day or review problems, and this is from that. So if I look at this one, of course I used an A instead of an X just because I can. If as A approaches 0, okay, well we're going to put our 0 in. 0, 0, 0 plus 4 is 4. Square root of 4 is 2. 2 minus 2 is 0 over 0. So this is indeterminate form, okay? But we can't factor this. The only thing we can do, which is backward of what we've learned, but we can rationalize the numerator. Totally weird. But we rationalized the denominator to make something not have a square root in the bottom. We do that to make it be written different. It doesn't change the problem, it writes it different. And that's what we're going to do here. So we're going to multiply the top by the conjugate, which is just a plus. And so we have to do that to the bottom as well. So we're going to multiply these together, okay? And I didn't show that full step, but if I multiply those, it would be a plus 4 squared underneath a square root, which does reduce to just a plus 4 right here. Okay, that times that is just a plus 4. Now that times 2 is going to be positive 2 square root a plus 4. Okay, and then I did this one times this one, then I switched to this one. Negative 2 times that is a negative 2 square root a plus 4, and negative 2 times negative 2 is a negative 4. So these two will cancel each other, and that's where I end up, and that cancels that with the a plus 4 minus 4. Okay, these make 0 right here. And then we multiply the bottom. A times this is A that. A times 2 is 2A. I didn't show it all the way out yet. I was like, where don't I have it as 2A? Oh, because the A's canceled. I left the A out so the A's could cancel because those would come 0. So really I'm going to have 1 over the A plus 4 plus 2. So the simplifying by far is just a little bit hard. And you could do it a little different than me and still get the answer. So this is written very different. And now if I put in the 0, I don't get 0 over 0. I get 1/4, which is amazing and gives me an answer. It's conjugate, by far the hardest ones. I think you might have one conjugate problem. And then you have a couple from a graph and you have some from this. So you also have videos that I post in with this lecture from the company as well. So there's more examples. Usually their examples are harder and I try to start from low to high. So, all right, that's all I got for you.